Hello, this is the first of two videos on exponential models, as shown here in the syllabus. A mathematical model is a simplified description of a real-world system using mathematical concepts. The process of developing a model is called modeling. An exponential model has the variable in the power. If the exponential function is increasing, it can represent growth. If the exponential function is decreasing, it can represent decay or loss. The general form of an exponential model is f of x is equal to k times a to the power of rx plus c, where k, a, r, and c are constants. The y-intercept is the point 0, k plus c, and the equation of the horizontal asymptote is y equals c. Remember that the constant a is called the base. The initial value is the value of the function when x is equal to 0. It corresponds to the y-intercept of the graph. So the initial value is equal to k plus c. Note that x usually represents time. The long-term value refers to the value of the function when x is large. If the function approaches the horizontal asymptote when x is large, then the long-term value is equal to the value of the asymptote, c. In this example, the population of a colony of bacteria in a petri dish is modelled by the increasing exponential function shown. In this example, the temperature of a cup of tea is modelled by the decreasing exponential function shown. In part A of this question, we're asked, what is the initial temperature of the kettle? So we need to find the initial value. We can do this by replacing time t with 0 in the function and simplifying the result, given the value shown. Alternatively, we can use the formula k plus c, where k is equal to 80 and c is equal to 20. So 80 plus 20 is still equal to 100. Or we can use the calculator. From the main menu, select Graph and type the equation into y1. So that's 80, and then pressing Shift natural logarithm button to access e to the power of, and then pressing the negative button, and 0.1, pressing the x variable button, and then the right cursor to come down, and then plus 20. Pressing Execute to enter the equation. Pressing Shift F3, View Window, to set an appropriate window. For x, I'm going to set -3 for x min, 30 for x max with a scale of 5, and for y, I'm going to set 0 for y min, 100 for y max with a scale of 10. Press Exit and then F6 to draw the graph of the function. The initial temperature is the y-intercept. To find this, press F5, G-solve, and then F4, y-intercept. We see that the value of y, or t in our case, is 100, the same value that we had before. So the initial temperature of the kettle is 100 degrees C. In part B, we're asked what is the temperature after 10 minutes. We can either substitute the value of 10 into the function and simplify the result. So on the calculator, from the main menu, select option 1, run matrix, and then type in the calculation. 80, shift E to the power of, and press the negative button, 0.1 times 10, and then the right cursor to come down, plus 20. Given the value shown. Or alternatively, we can use the calculator. This is a Y calculation. From the main menu, if I return to graph and draw the graph again, press F5, G-solve, F6 to get to the second page of tabs, and F1 for a Y calculation. Enter in the X value of 10 and pressing execute. We get the same value as before. So the temperature after 10 minutes is 49.3 degrees C, correct to 3 significant figures. In part C, we're asked how long does it take the kettle to cool to 30 degrees C. Again, we will use the calculator. However, it's also a good idea to write an equation, replacing the temperature T with 30. This is an X calculation on the calculator, so press F5, G-solve, F6 to get to the second page of tabs, and F2 for an X calculation. Enter the value of Y, which is 30, and press execute. Write down the value of X, which represents time T in our case. So it takes 20.8 minutes for the kettle to cool to 30 degrees C. In part D, we're asked to deduce the room temperature, where the kettle is kept, stating any assumptions that we make. After the kettle has been in the room for a long time, the temperature of the kettle will be similar to the room temperature. So the temperature of the kettle is its long-term value. To find this value, we need to find the equation of the horizontal asymptote. Using the equation y equals c, where c is equal to 20, the equation of the horizontal asymptote is t equals 20. Stating the long-term value, the temperature of the kettle approaches 20 degrees C. So therefore we deduce that the room temperature is 20 degrees C. Stating an assumption, this is assuming that the model can be applied until the kettle fully cools down.